Okay, so we have been trying to create single particle states in an interacting quantum field theory. To be more specific, in real scalar field theory, but whatever we do here can be applied to fields of other kind as well. So, actually we are very close to achieving our goal. So, let me quickly recap what we have done so far. Okay, so we have been trying to just take the same steps that we take in free field theory and see that if we arrive somewhere, and in that direction we had defined this object A dagger P with a subscript T, because this object depended on time explicitly. That is something I had asked you to check. No, I think I had shown you. Okay, this F, and then you have this time derivative operator which acts both the ways, okay, which I defined last time, okay, where F is defined as following: some factors. Okay, remember this omega p, when you write it will be omega p square is equal to p square plus mp square, where mp is the physical mass, okay, not the mass parameter in the theory, but the physical mass of the particles which you will get in this theory. Okay, this was the definition of this, and we had found explicitly that if you take this operator and act on the vacuum of the interacting theory, you create a linear sum of all possible states. Okay, and let me write down all these factors for easy reference. There was a 2 pi cube, and then we had sum over all the states, single particle states, vacuum, everything else. Okay, so that's this summation over alpha, and you had this delta cube, and then there were some other factors. Omega p t, okay, times alpha, or maybe I'll change the order of this compared to last time. I had alpha here, then field phi at 0, and then this omega. So this is the this matrix element of phi in these two states, and then you had ket alpha. Okay, so apart from all these other things, you see that you have to sum over ket alpha. Okay, and I had also argued that vacuum doesn't contribute. Okay, so out of this alpha you can drop the vacuum, because we argued that this delta function doesn't hit for vacuum, because p of the momentum of vacuum is 0, and since p is arbitrary, that delta function doesn't contribute. So from this ket alpha, ket omega drops out. So you are left with sum over states which are single particle states and multi-particle states. Okay, so here let me write not equal to omega. Not a great notation, but this is what it is. Okay, so good. Now we have to look at Let me remove these also. How do I remove? And this also. Okay. So recap is over now, and vacuum is also out of the equation. Now we have to look at the contribution of single particle states and multi-particle states. Where when I am saying multi-particle states, I mean states, if you are thinking in terms of Schrodinger picture, then states at time t equal to minus infinity, where we have assumed that these states represent particles localized in space far apart from each other. Okay. Okay, so now I will make a note here which will be useful. Okay. So let's start with multi-particle states. Okay, then I will come back to single particle state. So let's first deal with multi-particle states. So suppose I am looking at this state. Okay, then the total momentum, or the momentum of this state. Okay, and what is the momentum? Is the generator of the translations. So if you look at the generator of translations in your interacting quantum field theory and take that operator and act on this state, you will find that this is an eigenstate. Okay, this is how we had constructed this, and the momentum P will be equal to this. Okay, this we have been doing for quite some time. Okay, so hold on. Okay, so that's the momentum of this state, and it will have some energy which I will call as omega alpha. Okay, I'll leave it as alpha. But alpha means this. Okay, not the best best notation, but you understand what I mean. Okay, so energy will be omega alpha, where alpha is the state. Okay. Okay, now you might already be aware of, but even if not, there is no worry, that energy of a multi-particle state with total momentum P, which is this, okay, will always be larger than the energy of a single particle state with the same momentum. Okay. So if you had another state which is this, which is a single particle state, okay, and let's say its corresponding energy is omega P, and this one let me write slightly. So by this okay. So let's say for this multi-particle state the energy is omega. Okay, a temporary notation just to help me in telling what I am saying. So by putting all this, it's clear that I am not talking about even better. It will be, I think, this is still confusing. Let me write as with this way. Okay. So even though the energy of this state, the momentum of this state is P, okay, which is sum of these, and for the single particle state I am taking the momentum to be the same as here. Okay, so for both the states, for this multi-particle state and the single particle state, for both of them the momentum is P. Nevertheless, the energy of the multi-particle state, which is this one, will be higher than omega P. Okay, that's a claim I am making. It might be intuitively clear, Even if not, then I will show you. Even if it is, I will show you, not even if not. Okay, this where okay, so this I will show you, but for now I will utilize this result to do something very nice. Okay, so the point is, energy of a multi-particle state and a single particle state, okay, that difference is positive for same momentum, total momentum of these two states. Okay, so how can I utilize that? Well, let's see here. Now you look at this exponential, okay, and we have played such games before also, long before in the previous course. So here you have this exponential. So as far as the states which are multi-particle states are concerned, it's clear that omega alpha, okay, is greater than omega p, okay, because you are given some p, and omega p is what? Omega p is right. That's the energy of a single particle state. So that's omega p corresponds to energy of a single particle state with momentum p. Now you have omega alpha here, and I am right now looking only at multi-particle states. Okay, then omega alpha will always be greater than omega p. Okay, so this object omega alpha minus omega p is positive. Okay, that's what I want to use now. I'll show it later, but that's what I want to use. Now, omega alpha minus omega p is greater than 0 for this multi-particle state. Okay, so let's see how to utilize this, but before I can do that, I have to make one correction. So there is a mistake somewhere here. Yeah, here. This sign is not correct. It should be plus. Okay, so make this correction. Let's see whether I can find out where it was before. Plus here. And this is okay. You see, it had a e to the I omega alpha t. There was a plus sign here. Okay, so omega alpha came with the plus I. So it should be coming with a plus I, not with a minus I. Okay, so that was a mistake, and that was creating trouble for me. Now this should be fine. Plus I and okay. Good. So this being corrected, so we have omega alpha minus omega p. Okay, very good. So here we have this term. Now I want to get rid of all the multi-particle states, and actually I can do so by playing with this t. Okay, so I will choose a t such that this exponential factor provides the damping and it kills the entire contribution. Okay, so for that what I'll do is I'll take t equal to minus t, where t is capital T is a large time, so it's a large negative time. Okay, 1 minus I epsilon. Okay, where epsilon is a positive number, small and a positive number, but a fixed one. Okay, you choose whatever you like, but keep it fixed. So if you do so, then what happens? Let's look at the exponential. E to the I omega alpha minus omega p t, and now put t equal to minus t 1 minus I epsilon, where epsilon is greater than 0, and t I will eventually take to infinity. So if I do this, then I get e to the I omega alpha minus omega p times minus t plus I epsilon t, okay, which is same as e to the minus I omega alpha minus omega p t times I from here and I from there will give you minus 1. I square is minus 1. So minus omega alpha minus omega p, okay, epsilon t. Now understand why I made this choice, okay, for this t. If I choose a plus I epsilon, then it will not help, because then I will get a plus sign here, and you'll see in a moment why I need a minus sign here. So okay, epsilon is fixed, some small number but fixed, and now I am going to take t going to infinity. If t goes to infinity, this provides a damping factor and gives you 0, okay, and kills the entire contribution. Why? Because epsilon is positive, t is positive, omega alpha minus p is also positive, and that's crucial. So this entire thing here is positive except for the minus sign. So it's an exponential of a large negative number, and which is a very small number. So in the limit capital T goes to infinity, this exponential goes to 0. Okay, so this damps out the contributions coming from multi-particle states, or rather kills. Okay, that's very nice, because now vacuum is out, multi-particle states are out, and only single particle states are left. So let's go back here. So in this sigma alpha, now I have killed the vacuum, this is out, and all multi-particle states are out. What is left is only single particle states. Okay, so let's look at them. So for a single particle state, omega alpha will be equal to omega p. Okay, why? Because alpha p alpha will be forced to p by this delta function. I mean, that was true earlier also. Okay, but earlier energy of a multi-particle state was different from a single particle state. Actually, it was larger than a single particle state. But now, because omega alpha refers to a single particle state with momentum p, then the energy of omega alpha will be same as omega p, because the momentum of alpha is same as p. Okay, so this exponential provides you a factor of 1, because e to the 0 is 1. So there is no damping, and you get contribution only from the single particle states if you take t to be minus t 1 minus I epsilon. Okay, so good, this is a nice moment, because we now know how to create single particle states. So let me write this down. This nice thing. So, what I have shown you now is that if you take this operator A dagger of P, okay, with, okay, let me, A dagger T1 minus I epsilon P and act it or hit it on the vacuum, then I get the following. What do I get? I get okay, I'll just write down the answer. I'm going to cancel out few factors of omega p that you can also verify. It's so I'm not going to do the algebra. It's trivial. So you should get this times 1 over 2 omega p in the square roots, and then you have p phi 0 omega times this single particle state. Okay. So, everything else is some number, these are numbers, complex numbers, but then you have in principle complex numbers, but then you have a single particle state here. Okay. So, the goal has been achieved. I will write it in a more familiar form. So, I will write it as, I will take this root 2 omega p to the left hand side. So, 2 omega p in the square roots times A dagger of T1 minus I epsilon with an argument p acting on omega gives you 2 pi 3/2 times this factor times p. Okay, this is for your interacting theory, interacting scalar field theory. Okay, and real scalar field theory. And now let's compare this with what you had in the case of free theory. In free theory, we had the following. So remember, A dagger in that case did not depend on time at all. So there is no subscript here. And when it hits the vacuum, you get a single particle state. Okay. So it's exactly the same thing except for these factors. Okay. Okay, good. So now I make a claim that this factor actually does not depend on P at all. Okay, so I claim that this is independent of P. Okay. So no matter what the momentum what is the momentum of the single particle state, that object remains the same. Okay. So if that is a constant, independent of P means it's a constant. Okay. So I will call it the following. So it's a constant, and I define that constant to be this root z. Okay. And also divided by 2 pi 3/2. Okay, it's a constant, so I am defining that constant to be equal to this. I am calling root z divided by 2 pi 3/2, and the reason I put 2 pi 3/2 is this factor okay, because now I have so this is equal to root z divided by 2 pi 3 halves. So this 2 pi 3 half will cancel this 2 pi 3 half, and you will be left with root z times this single particle state. Okay, and if I take that root z to the left hand side and combine with a dagger, okay, so you'll have a dagger divided by root z, okay, and then you have exactly this form as in the case of single particle state. So let me write it down. So you'll get 2 omega p a dagger t1, sorry, minus t, did I put a t? No, minus t, okay, minus t1 minus epsilon p, and then over root z, okay, where z is a constant. We'll talk in a little bit more detail about z later, times what was here, vacuum. This is equal to a single particle state. Okay. Okay, so this is for your interacting theory. Let me write the equivalent thing for free theory. Okay, excellent. So what we have basically done is we have see here, here when I wrote these summation over alpha, all these states ket alpha, okay, these ket alpha were assumed to be the basis states which were in states. Okay, you can choose out states or in states. So here they were assumed to be in states. Okay, so all this ket alpha, they were in states. So what we have done here is we have created a single particle in state. Okay, and how did we achieve that? Sorry, here, how did we achieve that? By operating with this operator. So I will give it a name. I'll call it A in dagger P. And what is that? That's just a dagger of P with minus T1 minus I epsilon. Okay, not nice. Divided by root z. Okay, that's this. So we have learned that we can create single particle states by acting with A in dagger on the vacuum of interacting theory and get these single particle states. Okay, so our goal is achieved and now we are in business, but I should provide you with two proofs that are still pending, that energy of a multi-particle state is higher than the energy of a single particle state if both the states carry the same momentum, and also that this object is indeed a constant. Okay, it's independent of P. So let's do that now. So first is that E alpha is greater than EP if ket alpha is a multi-particle state. State with momentum P. Okay, so I'll show this to you for a two-particle state, and from that you'll be able to convince yourself that this is true in general. So let's take ket alpha, okay, and I'm saying it's two-particle state. So, one of them has momentum p1 and another particle has momentum p2, and the sum of the two is what is p. Okay. And the particles have masses mp, okay, mp physical masses. So, what's energy of the state alpha? Omega alpha is equal to, so remember these particles, the energy and momentum of these states are same as that of two particles which are non-interacting with each other. So, there is no interaction energy and only kinetic energy associated with their momenta. So, it will be for particle carrying momentum p1, it will be this, and for particle carrying momentum p2, it will be p2 square plus mp square, and I should add to get the total energy. Okay. And the single particle state with momentum p will have momentum p square plus mp square root, but p is same as p1 plus p2, right? Because both the states, single particle and multi-particle states, have the same value, have the same momenta, and p is this. So, I will write it in this form. Okay, this p is for physical, this is not the momentum, this subscript. Okay, so since both omega alpha and omega p are positive numbers, okay, I will just look at this this difference rather than looking at omega alpha minus omega p. Okay, it will be slightly easier. So, what is this? Omega alpha square is this square plus that square plus 2 times okay minus square of this, and square of this will be this square plus this square. So, this is p1 square minus p2 square minus 2 p1 dot p2 minus mp square. Okay. So, this is this object mp square plus 2 minus 2 p1 dot p2. Okay. Good. So, let us see. So, this is positive anyway. The only thing is we have to worry about this difference. So, here the largest value this takes is 2 p1 square in the square root or magnitude of p1 times magnitude of p2. Okay, this is not equal to, this is the largest value it can take. Okay, because this is a dot product and cos theta will be 1 when both are in the same direction, and in that case you will get this. Okay. So, this is the maximum you can subtract out of these two terms, and you see even then this term is larger than this because you have this mp square added, which means that omega alpha square is greater than omega p square, okay, because this right hand side is positive. And since both are positive, omega alpha and omega p, we conclude that omega alpha is greater than omega p for two particle states. Okay. And that is what we had utilized in here, okay, when we wanted to damp out all the multi-particle state contributions. And also note that here T is a large negative time. Okay, so it's really in the far past. Okay, so this operator A dagger is creating. If you are looking in Schrodinger picture, then it is creating single particle states in the far past. Okay, so that one of the pending proofs is done. Let's go to the next pending proof. Also, that one is also easy. So I'm going to prove this now. So I will show that if you take omega phi 0 p, okay, this object and that object, they are just complex conjugates of each other, okay, because phi is real. So it doesn't matter whether I show this is a constant or that is a constant. And whatever I am going to do, you can do it for this. There is absolutely no difference. So I am going to show that this is equal to this some other p prime. Okay. Now, given a single momentum p, you can arrive at another momentum p prime by doing a Lorentz transformation. Okay. So suppose you have a momentum p like this, and momentum p prime is in that direction. Okay, so suppose you were looking at a particle, single particle state which has momentum p, and that p is in that direction, and suppose you have another single particle state which has momentum p prime and p prime is in this direction. Well, you can, and suppose the magnitudes are the same, then you can arrive from this one to p prime by doing a rotation. Okay, you just have to do a rotation about an axis perpendicular to this to the screen of your laptop or whatever screen it is. Else, if let's say another possibility is that this p prime has a larger magnitude. Okay, so in addition to a rotation, you will also require a boost. So once you have done a rotation, then you do a boost, and by doing so, you will be able to increase the velocity or equivalently the magnitude of the momentum. So you can reach from p to p prime by a Lorentz transformation. Okay, and that's what I am going to use. So let's say the Lorentz transformation that is needed to go from p to p prime is parameterized by the parameters lambda. Okay, so lambda is a matrix whose elements give you the angles of rotation and the boost parameters. Okay, so lambda contains all those parameters. Okay, because that's all you need. So rotation will change the direction of momentum and boost will change the direction of the magnitude. So lambda, let me write matrix containing the rotation angles and boost parameters needed to go from p to p prime. Okay. Good. So that is fine. Now I am going to utilize the fact that under Lorentz transformation, the vacuum remains invariant. So here is the vacuum of the interacting theory, and the operator, remember we are doing quantum mechanics, so the operator u, okay, that carries out this Lorentz transformation lambda, okay, so u of lambda, when acts on vacuum does not change the vacuum, okay, so that's, it remains invariant. that we have already assumed. So that will be one input, and second input will be the fact that phi is a scalar field. So if you take phi of 0, okay, where 0 is for t and space both, then doing a Lorentz transformation will give you again the same thing back. It doesn't change. Okay, by a scalar we mean an object which doesn't change under that transformation. So how do field operators transform? Again, quantum mechanics, they will transform like this. Okay. So what do we have now? We want to look at this object. Let's look at this object. So omega what am I doing? Yeah, correct. Omega, and then instead of phi 0, I will write this left hand side because they are the same things. Okay. So this is equal to this, but then U acting on vacuum gives you vacuum, so this remains unchanged. So this is vacuum. Then you have phi 0, and then you have U acting on the ket P, which is U lambda acting on momentum. So that's the state. So all I have done is I have, instead of writing this operator acting on the ket, I have now written the ket. The ket is the one which carries momentum U, the momentum you get by changing P to lambda P. Okay, so that's the notation here. So that's the ket, okay, and which is what we call P prime. Okay, so you see that I have arrived at the right hand side, and thus the result is independent of the P. Okay, because no matter what P prime you choose, you can always show that omega phi naught P is same as omega phi naught P prime. So that's a constant. Okay. This implies that okay, and that is what we have used earlier. Okay, when we where was it? When we wrote that this is a constant. Okay, excellent. So now we know how to create single particle states in an interacting theory, and the next thing you should be wondering about is how to create multi-particle states, and that should not be very difficult once we know how to create a single particle state. And then also you should ask how to destroy particles. Okay, remember we had in free theory operators A and A dagger created single particle states, and A would remove particles from the state. So we would also like to have those kind of states sorry, those kinds of operators. And once we know how to create multi-particle states, we would love to throw them at each other so that they can scatter and produce something else in the final state, and then we can ask what's the probability of creating so and so final state when you collide so and so particles in the initial state. Okay, so these will be our next goals, and we will meet in the next video.